Welcome back everyone. In this lecture we are going to construct rational numbers from integers. So, let us recall that we have this set of integers which are actually parameterized by the following elements. So, you have these natural numbers which are listed as 0, 1, 2 etcetera, and then their negatives which are minus 1, minus 2 etcetera. So, we will write it as 0 plus or minus 1 plus or minus 2 plus or minus 3 and so on. Now, the most important thing is that we may be able to actually multiply two integers, but it may happen that we may not be able to actually multiply two integers and then get the number 1. Okay. Sometimes it is important to actually get solutions for some equations like this. So, let us take for example 2 inside the integers. Now, we want to find a x such that 2 x equal to 1, and it is not hard to see that. So, maybe I will leave it as exercise that there is no x in integers such that 2 x equal to 1. So, that means in order to get solutions for this equation, so one has to actually kind of go beyond integers. So, that is where the rational numbers actually comes in. So, we want to actually kind of look for something that actually looks like 1 by 2. Okay. But how to actually interpret this 1 by 2 and then how to construct natural numbers from the scratch only with the information about integers. So, one way to do that we need to first of all find different ways to write the rational numbers. So, let us begin with something like we commonly do. So, we take the set of rational numbers. So, by definition we just actually take it as it is a ratio between two integers like a divided by b, where a comes from g and then b comes from this non-zero natural numbers. So, let us actually take it to be non-zero integers. Okay. So, one can easily see that any rational number can be written as ratio between two integers with denominator being non-zero. But the problem with this interpretation is that like before, two different tuples may actually give us same rational number. For example, 1 by 2 could be same as just 2 by 4 and which is same as 4 by 8. So, this could happen. So, somehow if we are actually starting with integers and then want to construct rational numbers, and this way of interpreting rational numbers suggests that we should consider as before z cross z difference 0 and then identify certain elements using some equivalence relation. And the idea indeed comes from the fact that the equivalence classes related to the pair a comma b should interpret this a by b. Okay. That is where actually the motivation comes from. So, a comma b should be interpreted as or corresponds to a by b. So, this is the idea. Okay. So, once we understand the idea, then it is easy to actually work with the set and the equivalence relation. So, what will be the set? The set will be z cross z difference 0, and then you define this equivalence equivalence relation on this z cross z difference 0 as follows, and you say that a comma b is related to c comma d if we are expecting a comma b to be same as a by b and c comma d by is same as c by d. So, we want this to be equal in the world of rational numbers. So, this is same as saying that so because we do not know what is the division, but what we can do, we can actually multiply in cross way, then we get that AD is same as BC, and this is something we understand in the integers world. Okay. So, this is something we do not understand, but this we understand. So, we use this AD equal to BC as an equivalence relation between this A comma B, C comma D. So, we just define that A comma B related to C comma D if AD is same as BC. So, this is purely motivated by the fact that A comma B corresponds to A by B. Okay. So, now again it is a routine thing to check that this is indeed an equivalence relation. So, tilde is an equivalence relation on this G cross G difference 0. So, now as before what we did for integers, we are going to define the rational numbers to be this set modulo the equivalence relation that we had defined this. So, you take the corresponding quotient set, that we are going to call it as the set of rational numbers. So, this is for us the set of rational numbers. So, like I said, if we work little bit backward, what we have done indeed, we have defined this map from Z cross Z difference 0 to Q, and then we have taken the tuple A comma B and then send it to A divided by B. And then if you look at this map I, then the equivalence clause related to this A comma B is nothing but I inverse of this A by B. So, that is what indeed happening in the background, but we can't use this because we do not know what is the definition of Q. So, that is why we have taken this as definition. So, you take Z cross Z difference 0, then go modulo this equivalence relation, which is motivated from interpreting the tuple A comma B to this A by B. So, now as before what we are going to do, we are going to define addition and multiplication on this quotient set, and that will make this set of rational numbers interesting. Indeed, it will make it as a field, that is what we are interested in. So, as before what we need to do, we need to embed G inside Q, and we need to find a nice parametricing set for Q, and then we also need to actually define what is addition and multiplication on Q. So, let us start doing that. So, first to start with the definition of addition. So, if you actually recall, we want to interpret the tuple A comma B as A by B. So, then if we are actually doing that, then A by B plus C by D, we know how to add this using the usual rule on rational numbers. So, A by B plus C by D is indeed given by AD plus BC divided by BD. Okay. So, this is the addition supposed to be on rational numbers. Similarly, A by B times C by D should look like AC divided by BD. So, in integers, if you recall, the addition was easy to define, the multiplication was little bit complicated, but here you can see that the addition is bit complicated because we are working with the rationals, and multiplication is somewhat easy. Okay, this motivates us to actually define the addition as follows. So, define the addition between the two classes as follows. So, this is exactly given by AD plus BC comma BD, and similarly the product is defined to be AC comma BD. Okay. So, this is how the addition and multiplications are defined. So, this tells us that we have addition and multiplication on rational numbers. So, now we need to check what are the basic properties this actually satisfies. So, for example, the addition should be a binary operation from q cross q to q, and similarly multiplication must be a binary operation from q cross q to q. So, not only that, addition will satisfy commutativity, associativity and existence of identity element, which will be 0, and additive inverse. And similarly, with respect to multiplication, we will have commutativity, associativity and existence of multiplicative identity, which will be 1, and we will also have the existence of multiplicative inverse for all non-zero elements of Q, because we wanted to solve equations of the form 2x equal to 1, okay, and such equation will be solved for all elements of the Q difference 0. So, maybe take it as exercise. This is the only hard exercise, that for all x in Q difference 0, there exists y in Q difference 0 such that x y equal to 1. Okay. And indeed, this element will be unique. So, that is not very hard to actually see. And all these properties will make actually this q plus dot into a field. And of course, we have this addition and multiplication. These are two different algebraic operations. They should be interrelated, and that will be related by what is called this distributive laws. So, the distributive laws will look like something like this. The distributive laws, it is exactly what we had it for the integers, that x into y plus z should be same as x y plus x z, and this should be true for all x y z coming from Q. Okay. And all these properties will make this q plus cross into a field. So, that is something like I am not going to check, I am just telling you early. So, in particularly we will see that Q with respect to the addition. So, this becomes abelian group, and Q difference 0 with the multiplication, this also becomes abelian group. Okay. So, these properties are already there, and Q plus cross, this is also commutative ring. More than that, this is indeed a field. So, if you list all the properties that are satisfied by addition and multiplication of these rational numbers, so that is what actually defines a field. So, now it is customary to write that given x y in G in Q, that x minus y to be just x plus minus y. So, this is also there. So, now how one can actually embed the set of integers inside Q. So, what one can do, one can just take a and then send it to the class a comma 1, and that is going to be the image of a inside the set of rational numbers, and it is easy to check, this is indeed a injective map, and this map indeed preserves all the algebraic operations, like a plus b will be mapped to the class a comma 1 plus the class b comma 1 and so on. Okay, I am not going to check any of those things, all of them are actually easy to check. If one is seeing it for first time, it is better to check all these notions. Okay. So, not only this, one can actually define the order on this Q. So, like the integers, the order will be defined as follows. If we take x comma y in Q and we want to say that x is greater than or equal to y. So, if you think about it, then we expect that x minus y should be non-negative. So, that means that we can say that x is equal to y plus some a with a is greater than or equal to 0. But what is the meaning of a being greater than or equal to 0? Recall that any element of Q is of the form the bracket a comma b. Okay. So, any element looks like an equivalence class bracket a comma b, and what we can do, we can actually rewrite this as a divided by b. So, this is the standard notation that we actually use. So, now once we use this notation, it is clear that what will be non-negative elements in Q, which is usually denoted by x plus. So, this is going to be all possible a by b inside Q such that both a b they should be non-negative, and of course, b is non-zero, otherwise we will not be able to define a by b, and we demand that both a and b are non-negative. So, in this case we can actually define what is called non-negative rational numbers. Now, given a in Q plus, we write a is greater than or equal to 0. So, that is what I have used here, and this is going to define order on Q, and one can again check that this order satisfies the basic properties of order that we have seen for integers. For example, it is a partial order, and whenever you multiply with negative, the order will get reversed, and it preserves addition, and it preserves multiplication if you multiply by non-negative rational numbers again, and so on. So, all those basic properties again satisfied here. Okay. So, this is actually this is how one actually gets the rational number. The upshot is, so we started with the natural number, from that we wanted to construct integers, and then we wanted to construct rational numbers. So, natural numbers, if you think about, they are like natural. So, they are related to counting, but integers somewhat it demands that sometimes we will have a equation like x plus n equal to 0, and we want to solve that equation. By solving such equations, so one actually construct integers, if we think about it. Then we, so that is actually something to do with addition. So, that is why, like from natural numbers, we have ended up only by completing this additive part, we got the integers, but the multiplication of natural numbers naturally carried to the integers. So, that makes this integers into a commutative ring. But here the multiplication again is not complete. So, we may have a equation like 2x equal to 1, and we may not be able to solve inside the integers. So, to complete that, we had to go from the integers to rational numbers. So, that is where actually we are getting indeed a field which actually in a way completes both this additive and multiplicative structures. So, in more technical terms, so that are used in algebra. So, this is indeed a monoid with respect to addition, and if we are completing this, what we are getting is indeed a group, and if we take this n plus with this multiplication, from here what we are getting is indeed G plus cross, this is a commutative ring. And if we complete from here, then what we get is Q plus cross, which is a field or a quotient field. Okay. And if you think about it, this is where like most algebra happenings, because there are two operations, they are interrelated. So, fields are the best places to work with. And from here, if we do bit more analysis, then we will be actually getting what is called the real numbers. Again, the real numbers will be a field, but it will be a complete field, because there is a metric that we will be defining on Q, and that distance will be completed, and then we will be able to construct the real numbers. From reals, so one actually goes to what is called complex numbers, which is again a field, and complex numbers are motivated from solving much more complicated polynomial equations. So, from here to here we solved somewhat linear equation, actually monic linear. From here to here we solved all possible linears, because including non-monics. From here to here we are actually doing what is called completion. So, completion of a metric that is introduced on the rational numbers, and from R to C we try to solve all possible polynomial equation. So, this is how we reach all the way to complex numbers. So, that is how the complex numbers indeed invented. Okay. So, at least for this course we will not go beyond rationals. So, we will be actually only working with natural numbers, integers, and rationals. We will not even touch the reals or complex numbers. Some places we may need to actually use bit of real numbers and complex numbers, but whenever it is required we will actually come back to that. But from very basic HFC axioms we have actually constructed natural numbers, integers, and rationals from the scratch. So, we have not assumed anything, we have constructed everything from the scratch, and we have also told like how to work with the basic operations of these sets. Okay. So, this is all about set theory. So, after that after this what I want to do is actually basic counting problems. Okay. So, we want to actually get into combinatorics. So, we will start with very basic counting problems and then move on to actually some basic techniques that are used in combinatorics to count some important sets that arises in mathematics. And then later what we will do, we will actually get to what is called graph theory, which is a very much a discrete structure, and that is somewhat important for us because many interesting discrete structures that will be like coming from the graphs. So, we will spend some time on basic graph theory, and then we will not do much on graphs. Maybe I will spend like 2-3 hours of lectures and then do some basics of graphs. Then after that we will get into basic algebra, like bit of number theory and then some applications of group theory. Anyway, so let us start with some basic counting problems. So, we will actually start with very elementary counting principles. This may actually all of them sound so elementary, it will be like easily proved. So, most of the things I will not prove it here, because these are all very basic statements. So, let us start with these basic counting principles. So, there are like 4 principles. So, the very first principle is called what is called sum rule. So, what sum rule says, so whenever you have a set which is actually disjoint union of sets, then the cardinality of given set will be sum of cardinality of individual sets that actually form that set. Okay. More mathematical term, if S is disjoint union of Si, let us say from 1 to t. So, note that all this S1 etc. St are disjoint sets. So, with this then we have that the cardinality of S is exactly given by summation the cardinality of I range from 1 to t. Okay. So, since we are only interested in the counting problems, we are going to assume that all the sets that are involving in these lectures, they are all finite unless otherwise specifically specified. Okay. So, now we have this very basic sum rule which says that if you start with the disjoint sets, the counting the total number in the union will be same as summing over all individual cardinality of the sets. So, how one can actually use this sum rule in practice is that we actually choose a property, let us say EI, so that preclude each other. So, let us actually start with the property EI. Let us say for I varying from 1 to t, they preclude each other. So, that means if one occurs, the other properties do not occur. So, that is if one occurs, so then other properties do not occur. So, they are mutually exclusive. So, that is what it means. So, now what we will do in practice, we will define a set Si where you collect all the elements from the given ambient set capital S such that this X has this property Ei. Okay. Since the way we have actually chosen the property, if one occurs then the other properties do not occur, that would imply that these Si's are all disjoint. So, then this S will be just S, let us say all the elements of S must satisfy at least one property, then that would tell you that the S is exactly union of Si. So, that would tell you that the cardinality of S will be the sum of the cardinality of Si. So, this is indeed very important basic rule in counting. So, now let us see that how one can use this in an example. So, let us take a n set. So, let me denote that by In. So, which is a set 1 to n that has n elements. Such a set is called n set. So, now what we will do? We will actually choose all possible k subsets of this In. Okay. Actually, one can work with general capital X, not necessarily with In. So, let us take capital X, which is given by x1 etcetera xn, which is the n set. So, now let us take S to be x choose k. So, that means this is the set of all k subsets of x. So, that means you collect all possible subset A of x such that the cardinality of A is k. So, now we know that the cardinality of S is nothing but n choose k. So, this is something one can verify directly by induction, maybe that I will leave it as exercise. So, the exercise is that use induction and prove that cardinality of S is n choose k. So, now let us see how one can actually divide S into a union of two sets. So, what one can do? One can actually fix an element. One can fix an element A in capital X, and then we can construct these two sets S1, which is those subsets of A in X such that A contains this small element A and the cardinality of A is K. And similarly, one can write this S2, which is again all those subsets such that it does not contain elements A, element A and then the cardinality of A is K. So, now it is clear that S will be disjoint union of S1 and S2. And it is not hard to see that there is a bijection from S1 to the following set. Okay. So, maybe let me leave it as exercise. So, there is a 1-to-1 map or bijection which is given by. So, you take A and then send it to A difference A, which is a map from you take X difference A and then choose K minus 1 subsets. So, then this map A goes to A difference A gives you bijection between S1 and this known set. Similarly, you can see that there is a bijection between S2 and the following X difference A choose K. So, you can send A to A. Okay. And these bijections tell us that how to count this S1 and S2. So, the cardinality of S1 using this bijection you can see that this has exactly n minus 1 elements. So, it will be n minus 1 choose K minus 1. And similarly, the cardinality of S2 is going to be exactly this will have n minus 1 elements. So, it will have cardinality exactly n minus 1 choose K. So, now using the sum rule we get the cardinality of S equal to cardinality of S1 plus the cardinality of S2. So, that means we have proved that n choose K is same as n minus 1 choose K minus 1 plus n minus 1 choose K, and this is true for all n greater than or equal to K greater than or equal to 1. And this is what called Pascal identity, which one can prove using induction as well. But anyway, this two different way of counting actually gives different proof. Okay. So, the next rule is again somewhat elementary. So, the second rule is indeed what is called the product rule. So, which says that if S is indeed Cartesian product of S1 and ST, so then the cardinality of S is exactly equal to the cardinality of S1 times etcetera times the cardinality of ST. Okay. So, basically the cardinality of S is the product of cardinality of Si I range from 1 to T. And again product rule is very important. So, this can be verified using induction, because this will follow from the fact that the cardinality of A cross B is same as cardinality of A times cardinality of B, which I left it before as an exercise. So, now as an example you can see that if we are considering all possible n words over 0 comma 1, which is given by the Cartesian product of 0 comma 1 power n. So, this is the set of all n words over this 0 comma 1. So, if you take this to be your S, then the cardinality of S is exactly the cardinality of 0 comma 1 power n, which is exactly 2 power n. Okay. So, this is something we already know. Okay. So, the third rule is exactly is that it is the bijection rule. So, again it is clear that what is the bijection rule says. We already used the bijection rule. If there exists a bijection between the set S and T, let us call it F, Okay. Then the cardinality of S is same as cardinality of T. Okay. For example, we already have the bijection between 0 comma 1 power n and the power set of x, where x is given by, let us say, a1 etc. a n, which is a n set. Okay. In particularly, the cardinality of p of x is same as the cardinality of 0 comma 1 power n, which is exactly 2 power n. So, this is something we already checked. So, I am not going to repeat that. So, recall that the map is indeed defined to be, so you start with a here and then you define the tuple, let us say b1 etc. bn, such that bi is 1 if a belongs to a and 0 otherwise. Okay. So, this is the map that I already discussed a long time back. So, that gives you a bijective correspondence between p of x and 0 comma 1 power n. So, p of x is nothing but the set of all subsets of x. Okay. So, the fourth rule, which actually talks about counting two different ways. So, when two formulas enumerate the same set, then they must be equal. So, that is what the counting in two ways says, which is again we have used before. Okay. So, the counting in two ways, which tells you that when the two formulas enumerate the same set, then they must be same. For example, what one can do, one can actually count the following dots as follows. So, let us say I have n number of dots, I am considering this n by n matrix. So, where you have this dots are arranged as follows. So, let us just erase this. So, then what one can do, one can actually count it in two different ways. So, the total number of dots going to be, so the total number of dots, that is will be exactly n square. So, which will be same as what one can do, one can actually calculate via diagonally. So, we can start with this and then take this and then take this and so on. Then it is easy to see that this n square will be same as twice 1 plus 2 plus etc. plus n minus 1 plus n. So, this is going to give us the formula that 1 plus etc. plus n minus 1 is equal to n square minus n divided by 2, which is the well known formula for this 1 plus etc. n. So, indeed from this one can get that 1 plus etc. n is exactly n into n plus 1 divided by 2. So, this is what we are getting by counting the same set in two different ways, and this is actually somewhat very powerful and useful tool, and we will see some more complicated examples in the later part of the lectures. So, now we will actually stop here with this. So, later maybe in the next lecture I will actually do somewhat complicated counting that will actually tell you that counting in several ways that will actually help us to prove much more interesting identities. Okay, I will stop here. Thank you.